So we'll get back to some of these examples from class again today, and we'll look at the car connected with the boulder and the platform again. So just to redraw these FBD KD system, right, on the left-hand side, how we isolated the boulder and the platform is we cut the cable that exposed the tension in the cable. The other forces present would be the weight of A, the platform, and B, the boulder. So those are all our free body diagram forces. The kinetic diagram forces are going to be the mass times acceleration. We're told here that the truck accelerates to the left with a constant acceleration, and therefore we would have an acceleration upwards of the boulder platform combination. So that's going to be the mass of B, the mass of A, multiplied by the acceleration. And so we're going to sum forces in the y direction. We'll call up positive. The reason why we're going to do this is we're asked about the tension. So that's why we first drew the FBD KD, so we could show the tension. Now we can sum forces and create an equation that will talk about the tension. So we've got tension minus the weight of A minus the weight of B. Over on the right-hand side, we'll have the mass of A and B, so the total mass times the acceleration. If I just go ahead and solve this again, I get that the tension is equal to the weights plus the mass times the acceleration. And again, we know that the acceleration is up, so it's all added. So it means that the tension is larger than the static case. Right? In the static case, the acceleration would equal 0. And we don't have, we have a dynamic case. So it says that the tension is going to be bigger than the weight of A and B together. So we can see that it's not going to be 200, right? It's not going to be 1200. That is the total weight. So we know that it's going to be greater. And we go down to D and E. We're asked about the normal force between A and B. So we need a free body diagram KD system that has that normal force in it. And so we're going to draw the boulder free body diagram. We've got the weight of the boulder. Right? We've got the platform force that was pushing on the boulder. Right? That's the normal force that we're asked about in the question. And now over here on the KD side, I've got the mass of the boulder times that acceleration, right? Because it's sitting on the platform and the platform is accelerating. And so now I'm going to sum forces in the y direction. N minus weight of B is equal to mB times A. And now I've got that the normal force is equal to the weight of B plus mB times the acceleration, whatever that acceleration is. So if we look here, it talks about the normal force between A and B, right? That's that N that we're talking about right there that we've drawn. And so this one says it's 1,000 pounds. Well, I know that the weight of B is 1,000 pounds. And so I've got another term added to it, so that's not true. And the normal force is 1,200. It's not 1,200, right? It's going to be the weight of B plus mB times A. So chances of it being 1,200 were pretty slight because we need a certain acceleration to make that happen. So let's go ahead and look at another conceptual question here. What we have is two systems, very similar to each other. I'll kind of help with the drawing. I've got a block here, block A, connected to a block B. Both of them weigh 40 pounds. All right, in this other system, I've got a block C, right? That weighs 40 pounds connected to a cable, and a force is applied to the cable of 40 pounds. So what we're asked is about the acceleration of blocks A and C. So we can see that the acceleration of those blocks is obviously going to be directly related to the tension in the cable, right? If we were asked to neglect all friction forces. And so we'll draw the FBD KD for block A up here, and we'll see what I mean by that. To do it, I've got the tension, I've got the weight, and then I've got a normal force. And then block A is going to move to the right, so I would have the mass of A times the acceleration of A. So you can see, right, by just looking at the FBD KD, and by some forces in the x direction, the acceleration is going to be the tension divided by the mass. That's going to be true both for block A and for block C. It really won't matter. So let's go ahead and take a look at the tension over in the AB system. So to do that, we're going to draw the FBD KD for block B. And so we've got the tension. Right, I'm going to go ahead and cut it right there. That exposes the tension in the cable. I've got the weight of block B, and I've got that the mass of B times the acceleration of B is going to be acting down. And so what I'm going to do now is some forces in the y direction. And I'll call up positive. T minus the weight of B is equal to minus MB AB. And so I can now rewrite this for the tension, which is going to be the weight of B minus MB AB. And so remember, the weight of B is 40 pounds. So I would know that the tension is going to be less than 40 pounds. So if I kind of come back up here to our two systems, we'll zoom in. What we found is that the tension is less than 40 pounds in this system, in that rope, and the tension is equal to 40 pounds in that system. And so we would see that, right, since the acceleration and the tension are going to be directly proportional, right, we would know that they will not have the same acceleration. Right, block C will have a larger acceleration because it has a larger tension. Right, block A will not have a larger tension. Block A won't move. Block A will definitely move because there's going to be a tension. So there's going to be an acceleration. So that's not true. All right, so now our last one here, we've got this kind of revisits something we had done in class, and we had discussed a relative acceleration equation. So I'm going to rewrite that right here. And again, this is sort of a coming attraction for week 3, but the acceleration, this is a vector equation. The acceleration of block B, right, is going to be the acceleration of block A plus the acceleration of B with respect to A. This is called the relative acceleration equation. We're going to have a relative velocity equation as well. But this really tells us that block A and block B, because of the fact that they are touching each other and they'll remain touching each other, and block B is going to slide on that slope, then the relative acceleration, the relative between B and A, is going to be directed directly down that slope. And we, as we would remember from earlier, we have an acceleration of block A that we put in the going to the left. So we can redraw this, right? We can redraw the FBD KD system with block A with its acceleration on it, and then block B with an application of the relative acceleration equation. So we end up with the acceleration of A and then the relative of B with respect to A down the slope. So what we're going to do then is just sum forces in the y direction. We'll go up as positive. And so I end up with n minus the weight of b minus the weight of a is equal to, if we look here, we have one component from that relative acceleration vector. So that would be in the negative direction, minus mba b with respect to a. Now it's not the whole vector, but it's just the y component of the vector. So if I rewrite this equation, just bringing the weights to the other side, right, I find out that what it's asking us for is the normal force between block A and the ground. So it's asking us questions about N. And so first option is that it's less than the weight of A plus B. We can go ahead and look down here. I've got the normal force is the weight minus something. So that looks pretty good right there. It looks like we've run into it. The other one, it says it's equal to the weight of A plus B. No, we've got that negative term on it. And the other one is that it's greater than the weight. And it's not, because we've got a negative sign and we've drawn that acceleration in the correct direction.